Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 26, 2025, just yesterday. The standout result is a system that synthesizes up to 90 minutes of multi-speaker speech using next token diffusion, powered by a continuous speech tokenizer that achieves an 80 times compression boost over encodec while keeping comparable quality. The paper is titled VibeVoice Technical Report, and as we will see later, the implications for long-form dialogue generation are quite significant. In short, it blends an ultra-low frame rate tokenizer with an LLM-guided diffusion decoder to create natural, stable conversations with up to 4 speakers. Also, the authors shared a full GitHub repo. You will find the VibeVoice codebase, a pip installable package, demo scripts for Gradio and file-based inference, model links for 1.5b and 7b preview, sample texts, figures, Docker and Flash attention setup notes, FAQs, and an MIT license. On Hugging Face, you'll find VibeVoice 1.5b model weights, training details, and Python usage examples for generating long, multi-speaker TTS. The LLM backbone is 1.5 billion parameters. Alright, the last segment highlighted the code and model availability. Figure 1 presents 2 messages. The bar charts report subjective scores where VibeVoice 7b and VibeVoice 1.5b lead on preference, realism, and richness, and the scatter line shows output speech length scaling past 5,000 seconds. The combination matters because longer context often hurts quality, yet both models stay ahead. The star at the top right marks the length and quality frontier. So, Figure 2 lays out the end-to-end pipeline that made those long runs possible. The diagram shows user inputs as voice prompts and text scripts, which feed hybrid context tokens into VibeVoice and then into an LLM. The LLM outputs condition a diffusion head that predicts the next continuous acoustic token, so the acoustic decoder can render speech. The lower branch highlights semantic tokens guiding content, while the upper branch iteratively generates acoustic latents for up to 90 minutes. Alright, Figure 2 showed how the pipeline stitches text, roles, and acoustic latents together. Table 1 reports head-to-head results across subjective realism, richness, and preference, plus objective word error rates and speaker similarity. VibeVoice 7b posts the highest subjective averages and the strongest similarity score, while VibeVoice 1.5b achieves the best NEMO word error rate, so intelligibility remains competitive. Several commercial systems trail on the long-form set, which reinforces that the low frame rate tokenizer did not sacrifice quality. So, Table 3 compared reconstruction quality across tokenizers at vastly different token rates. The acoustic tokenizer reached 7.5 tokens per second and still delivered leading perceptual scores, with PESQ at 3.068 and UTMOS at 4.181 on test clean and strong results on test other. Encodec variants kept higher intelligibility by STOI because they used hundreds of tokens per second, but they paid a huge rate cost. The key message is that extreme compression still preserved perceptual fidelity, which unlocks very long contexts. Okay. The last table showed extreme compression without losing perceptual quality. Table 2 reports SEED test set results, comparing character and word error rates with speaker similarity across Chinese and English. VibeVoice 1.5b runs at a very low 7.5 frame rate, yet posts 1.16 character error rate in Chinese and 3.04 word error rate in English, with similarity around 0.744 and 0.689. The comparison systems use 25 to 50 frames per second, so comparable accuracy at 1/5 to 1/10, the rate signals strong efficiency. Wrapping up, 2 takeaways stand out. The ultra-low frame rate continuous tokenizer enables extreme compression without audible collapse, and next token diffusion conditioned by an LLM keeps long, multi-speaker dialogue natural for up to 90 minutes. The broader implication is scalable, podcast length, TTS, that is efficient and controllable. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.